Math 1325, we are up to section 5.3 today. And I want to show you a couple of things here. So 5.3 is higher derivatives, concavity, and the second derivative test. And then down here at the bottom, I now have 1, 2, 3, 4, 5. There's 6 last sections we do in the fourth unit. The first 3 units all have 7 sections. The last one's only got 6. So once we finish the third unit on November 11th, then we'll have 3 weeks, well, really 3.5 if you count Thanksgiving week, 3.5 weeks to do these last 6 sections, which is the 5 sections of chapter 7 we cover, plus 1 left over from 6.6. The fourth review and the tests are already created. They're going to be due on December 9th. And then we have exactly 1 week in the semester left at that point. And that last week is just for reviewing and taking the final exam. Also, if you go to the e-text, chapter 5, section 2, I got stuck, not really stuck, but I missed the end of that problem number 9. So since that last video, section 5.2, I went into the textbook here, and on page, this is page 291, if I go forward to 292, they have a definition box here for relative maximum or minimum, and after describing what's happening here, they have a little asterisk at the end that says, if a critical number is an endpoint of a domain of F, we only consider X in the open half interval that is in the domain. And then there's a little star here, and then at the very bottom, and like the fine print that a lawyer would have typed up, there is disagreement on calling an endpoint a maximum or minimum. We define it this way because this is an applied calculus book, and in an application it would be considered a max or min value of the function. So if you remember at the last video, section 5.2, on number 9, it turned out the 2 endpoints were also maxes and mins in that problem. And it caught me a little bit off guard because normally those are not considered max and mins. Relative max and mins only normally come from critical numbers. They don't come from the endpoints. The overall max or min of a function can come from endpoints, but not normally the relative max or min. And notice they even say there is some disagreement on this. Some textbooks do it, some don't apparently. So the reason they're doing it is, and I didn't know until I looked it up myself, sometimes what you have to do is just look things up when you get something wrong. But that was a problem where there was like temperatures over a 24-hour period, and it was a cubic graph that looked like this. So just at any 24-hour period you start keeping track of temperatures, there's an arbitrary starting point, even if that's like midnight of a day. And then the arbitrary stopping point is when you hit midnight the next day. That's your 24-hour period. But then you have another 24-hour period after that, and so on. It was arbitrary in the problem to just say we're going to check for 24 hours. If we just keep checking temperatures constantly and don't care about any 24-hour period, then the starting and stopping points wouldn't be so defined well. But they did do that here. So the ones I got were the 2 critical numbers that happened here and here. But if you were really tracking this temperature over 24 hours, and because it started here, there is no point anywhere else in the graph that's higher than that. So there's actually a section coming up later where we call that a absolute maximum, not just a relative maximum. Most books don't call this a relative maximum because it's not increasing on one side and decreasing on the other. It's decreasing on both sides at that point. It's not even a critical number either. So, but because they're saying in temperature, if that's the highest point the whole day, the whole 24-hour period, it never was hotter than that point, somebody who's tracking temperature would want to know that. And if the end point at the end of the 24-hour period, if that's the lowest it ever got, there's no other point lower than that in the whole 24-hour cycle. So somebody who's tracking the high and low temperatures, they would care about that is the point this textbook's trying to make. but I didn't even know that myself till I had to look that one up. Is why that problem number 9 had those two endpoints included with them. As soon as the first endpoint came up, then I realized they're going to probably include the second one too, and that did turn out to be true. Okay, so let's now go back to assignments 5.3. So we've done many versions of derivatives. This is the first time, though, that you're going to see what are called higher derivatives. So we go for a function f of x that's 3x to the third minus 7x squared plus 13x plus 9. So let me show you what you already know. The original function is 3x to the third minus 7x squared. We just have some polynomial function here. Plus 13x plus 9. We certainly can easily do what's called the first derivative, really. We never really referred to it that before, but the first time you take a derivative is technically the first derivative. And this is just your normal power rule. 3 times 3 is 9, x, and then decrease the exponent by 1. 7 times 2 is 14, x, decrease the exponent by 1. The derivative of 13x is 13, and the derivative of 9 is nothing. This is the derivative, and it tells us slopes of tangent lines. But somebody thought, what if I do a derivative of a derivative? We've seen in math before, like functions inside of functions, radicals inside of radicals. You can do a derivative inside of a derivative, basically. Just do the power rule again. What if you just did the power rule again from a derivative answer? 9 times 2 is 18, x to the first, and the derivative of negative 14x is negative 14, and the derivative of 13 is nothing. You can do a third derivative. The derivative of 18x minus 14, that's linear, so the derivative is just 18. And as soon as it gets to fourth or higher derivatives, if you put too many of these apostrophe marks, then it's hard to see them all. So after 3, then they just put it in parentheses as whatever number you want to do, 4 or 5 or higher. But the derivative of a constant is 0. And then for every derivative after that, this one would just be 0 forever. So I could do a 5th derivative, a 6th derivative, a millionth derivative, but once it hits 0, it's going to stay 0 forever. So whenever you're working with polynomials, each next derivative has an exponent that's 1 less than the previous one. Also, an application of this is, in physics, they deal with the position of an object moving somewhere. So s of t is the position function. Where's my object located in space? And then the derivative of position is velocity, how fast the object's moving. And then the second derivative of position, or the first derivative of velocity, is acceleration, how fast it's speeding up or slowing down. So this is an application in physics they do all the time, where you're doing higher derivatives, they call them, once you go past the first one. This problem wanted the second derivative, f double prime of x, that's red, f double prime of x, it's 18x minus 14. Once you get the second derivative, then you can plug in numbers for it. So now I can do f double prime of 0. Put 0 into this second derivative function. 18 times 0 is 0, minus 14 is minus 14. And then f double prime of 8, plug 8 in, 18 times 8, minus 14, 130. Later in this section, we're going to worry about what's similar to what we do with first derivatives. In first derivatives, we locate when is the first derivative 0 or undefined. Those are called critical numbers. And then we check values on each side of a critical number to see is the derivative positive one side and negative on the other, or vice versa. That tells us the function is increasing at first and then decreasing second, or vice versa. And that's when you get local maxes and mins. A very similar process happens with the second derivative. When a second derivative is positive, there's a certain concept for that. When a second derivative is negative, that's the opposite concept, and that's what we're looking for. We're going to get spots that are similar to critical points or critical numbers, and then we're going to hope maybe the second derivative is positive one side and negative on the other. That's coming up here in a second. Okay, same kind of problem, but now the original function is cubic. I mean, not cubic. The first one was cubic. Now we're moving up to a fourth power, quartic. So f of x is 3x to the fourth minus 4x to the third minus 3x squared plus 6. So do the first derivative with the power rule. 3 times 4 is 12, x to the 4 minus 1, which is 3. 4 times 3 is 12, x to the 3 minus 1, which is 2. 2 times 3 is 6, x to the first, and the derivative of 6 is nothing. There's the first derivative. Now do the second derivative, f double prime of x. 12 times 3 is 36, x squared. 12 times 2 is 24x. And the derivative of negative 6x is just negative 6 since that's linear. So this is the first answer they want. Then we're going to do f double prime of a couple of values that they're picking for us, but later we're going to pick our own values to plug in for. So 36x squared minus 24x minus 6x. 36x squared minus 24x, minus 6. Oh, yeah, I left off the x. Okay, duh. It's right there. See, there's a brain cramp type mistake that happened to anybody, although I did put it here. Negative 6x. Oh, wait, it is double prime, okay. Oh, yeah, that's just, wait a minute. That's no x there. Yeah, that's what's wrong, is I was thinking it was negative 6x, but I was right. It's minus 6. Okay, so 36x squared minus 24x minus 6. See, that's a case where I had it right on the scratch paper, and then I typed it in wrong and then got confused what I was even doing. But here's f double prime of 0. Put zeros in for both of those x's. That makes that all disappear, and it's just literally negative 6 for the answer. But what's more important later is that it's negative. A negative second derivative tells us something we're about to learn. And then f double prime of 2, if I do 36 times 2 squared, 36 times 4, minus 24 times 2, minus 6, 90. But more importantly, positive 90. So the second derivative is negative first, and then it's positive second. Something's happening in between there. The point where it changes from negative to positive is 0. That tells us that it hits 0 at some point in between there. Okay, what if you get a fractional exponent in number 3? X to the 6/7. First derivative would be 6/7. X to the 6/7 minus 1, but that could be 6/7 minus 7/7, which is negative 1/7. Then I can do a second derivative of that. 6/7 times negative 1/7 is negative 6/49. X to the negative 1/7 minus 1, which is negative 1/7 minus 7/7. That's negative 8/7. Negative 6 over 49, x to the negative 8/7. And in this scenario, you would just keep going forever. It would never hit 0. There's going to be a new derivative every time. So because you have a fractional exponent, it's never going to make the x disappear. You can see that the exponents, you're really just subtracting 7 from the numerator over and over again. So the next one would have an x to the negative 15/7, the third one. The fourth one would have x to the negative 22/7 in it. So it would just never stop. It would just be a different answer every time you did another derivative. So in some derivatives, if you do enough higher levels of them, sometimes you hit 0, and then it's every one after that's going to be 0. But sometimes you get a different answer forever every time you do a higher power. Or if you say your original function was e to the x, if you remember that one back in chapter 4, the derivative of e to the x is itself, and then technically times the ln of e and times 1, but those don't matter. So the derivative of e to the x is e to the x, and then as you went to higher and higher powers of derivatives, it's going to stay e to the x forever. So if I did f 100th prime of x, if I did 100 derivatives, it would still be stuck on e to the x. So sometimes they don't change, sometimes they hit 0 eventually, and sometimes they're just literally different forever. Not that any of that matters here, but... Okay, plug 0 in for x. 0 to any power is 0. And then 0 times anything is 0. So this equals 0 exactly. And what that's... type in integer, simplified fraction. Okay. Oh, no, I know it's wrong. Is because it's a negative exponent, it would actually be 0 in the denominator. So then it's undefined. So it wouldn't be 0 times it, it would be negative 6 divided by 0. So the negative 8/7 drops it to the bottom first. But here in a second, we're going to see that if the second derivative is 0 or undefined like this, that's a special case, kind of like critical numbers for first derivatives. Although it doesn't go by that same name. Now, 1 to any power is 1, but even if it's in the denominator, then it's not going to matter. So that's negative 6 over 49. So it actually is technically in the bottom, but 1 to any power is 1, so then you would have 49 times 1, which is 49, and then the rest would be the same, negative 6 over 49. Okay, negative 1, if you put this in the bottom... Negative 1 to the, well, if we did it, let me show you what's happening here, because it depends on the root. If you did square root of negative 1, that's equal to the imaginary number I. You can't do even roots of negative numbers. But if you do a 7th root of negative 1 to the 8th power, that's what negative 1 to the 8/7 power would be. And because we had negative 6 over 49, x to the negative 8/7. If I drop that x to the denominator, then it can become positive 8/7. And then it would look like this. The negative 6, the 49, and I move the x to the bottom to make it positive. Now I'm plugging negative 1 in. The 7th root of negative 1 is negative 1. Any odd root of negative 1 is negative 1. So then you would have negative 6 over 49 times negative 1 to the 8th power. Well, then any value to an even exponent is positive. So then it flips back to positive 1 times 49, which is 49. So just like when you're doing parabolas, x squareds, f of x squared... If you have f of x squared, f of x equals x squared for your function. If you do f of 2 or f of negative 2, the answer is the same both ways, because the even exponent makes the negative go away. So it turned out here that both f double prime of 1 and f double prime of negative 1, they both happen to equal the same thing, because the even exponent turns the negative 1 back to positive. Okay, here is one with an e in it. So the original function is 3e to the negative x squared. And it's the same directions as the first three problems. Find the second derivative and then plug in various numbers that they're going to give us. So fourth problem, f of x equals 3e to the negative x squared. First derivative, this is the exponential rule. The 3 is just a constant. Any exponential derivative is itself. Technically times ln of whatever the base is, but ln of e equals 1, so that won't matter if there's other stuff here. And then times the derivative of the exponent. The derivative of negative x squared is negative 2x to the first. So if I simplify that, I could multiply the 3 times the negative 2x and get negative 6x e to the negative x squared. So now if you want to do the second derivative, you've got two different functions of x here. There's a negative 6x that I'm going to consider to be the first function times e to the negative x squared, which is the second function. I have a function of x times a function of x. That's the product rule. So all these rules from chapter 4 can come up again. First, now the derivative of the second is what I literally just did a second ago without the 3 part on it. So the derivative of the second is this right here. So that would be negative 2x e to the negative x squared. First times the derivative of the second plus the second times the derivative of the first. The derivative of negative 6x is just negative 6. For here, you don't really have to clean this up too much. I will go ahead and do it though, because later we're going to need to, but you could definitely multiply the negative 6x and the negative 2x and get positive 12x squared. And then I could make this negative 6 e to the negative x squared. This is probably fine for the answer just like this. If somebody wanted to do a GCF, you could pull a 6 e to the negative x out. And that would leave you with 2x squared minus 1, literally. This whole thing is the GCF right there. Later, we're going to need to do this to see when it equals 0, but for now, we don't really have to, so I could just leave it in this first format. 12x squared e to the negative x squared, an exponent inside of an exponent. 12x squared e to the negative x squared minus 6e to the negative x squared. Plugging in 0, one nice thing is this 12x squared part. When you plug 0 in for that, 0 squared is 0, 0 times 12 is 0, and 0 times anything is 0, so it'll even knock this e part out. This whole front part will be 0. Now, plugging 0 in here does not make the answer 0, because even though 0 squared is 0 and there's no such thing as negative 0, you're going to have negative 6 e to the 0 is what's going to remain. So this whole part here does equal 0 because the regular x is going to turn into a 0 and multiply to 0 and make 0. But on this negative 6e to the 0, this part will equal 0, but it's e to the 0. It's not times 0, it's to the 0. Over here it's times 0, but in this part it's not. So anything to the 0 power is 1. And I can drop the front 0 because 0 minus anything is the anything. Negative 6 times 1 is negative 6. So just because you're plugging 0 in doesn't make all the parts disappear and go to 0. Or even become undefined necessarily. Now plugging 2 in, I'm looking in the blue part because I know it's going to happen already, but do not round into the final answer, then round to 4 decimal places. Because if you do e to a number like 2, or even if it gets squared to 4, it's not going to come out evenly. So then really all you can do is either leave it real messy with a bunch of e's and fractions in it, or use a calculator and round it to decimals. So you only round to decimals with a calculator if they ask you to do so. They are asking here. So from this part right here, I'm going to plug a 2 in everywhere there's an x. So 12 times x squared, so that's 2 squared, e to the negative x squared, squared. But I plugged a 2 in here and here. That was there and there. And then I'm going to plug another 2 in right there. So minus 6e to the negative 2 squared again. This was the 2 that got plugged in. So 2 squared here is 4. 4 times 12 is 48. This is just literally negative 4 right there. Notice that the negative is still there. The negative is not part of the exponent. Only the 2 gets squared. It's not negative 2 squared. It's the opposite of 2 squared. And then this would be another negative 4 right there. So if you have a calculator that has e on it, like right here's e. There's e, 2.71828 and so on. E, I can raise that to the negative 4th power. So this big messy decimal, that's this and this. So I need to multiply it by 48. Okay, and then, so now I need to subtract another one. So I guess I'm going to write this down. 879. If I did it in my graphing calculator, I could do it all at once. But 8791506. We're rounding to 4 decimals at the end, so if I carry like 7 or 8 decimals, that should probably be enough. So e raised to the negative 4 again, and then multiply by 6 or negative 6. So I need minus this decimal, 1098. (9383). So 0.8791506 minus 10989,303. And rounding to 4 decimals, 7692, but there's a 5 after that, so make that 2 become a 3. 7693. Approximately, because we worked in decimals here. 7693. So plugging integers like 2 into an expression that has e in it is always going to come out messy. So that's usually when one of the rare times they'll accept decimal answers. Okay, now I already showed you this, but now they want you to go all the way to the 4th derivative, the 3rd and 4th derivative. So you really can't jump to those right away unless you know it's one like e to the x, it's just going to be the same all the time. Or if you've already hit 0 at some point along the way, then you're going to know all the rest of the derivatives are 0. But I've got a polynomial function, 3x to the 4th plus 4x to the 3rd. Plus 3x squared plus 4x. Plus 3. Okay, they want the 3rd derivative as the first answer, but you're going to have to do the first 2 derivatives before you even get to that. So the first derivative, and this is just power rule over and over again, 12x to the 3rd 12x squared, 6x to the first, and 4. There's the first derivative. Second derivative. 12 times 3, 36, x squared. 12 times 2, 24x. And then just 6 for that part. Here comes the first answer. Third derivative. 72x to the first plus 24. 72x plus 24. Third derivative is linear. And now the fourth derivative is the derivative of this, which is easy because this is linear, so the derivative of it is just the 72 in front of it. And then if I did a fifth derivative, it would be 0, and then every one after that would be 0 as well, which may be why they're stopping after the fourth one. Okay, same kind of problem. Now we're starting with a fifth power. 5x to the fifth minus 3x to the fourth. Two x cubed plus 7x squared. Plus 2. There is no x to the first term, and that's okay. Okay, first derivative. 5 times 5, 25. X to the 5 minus 1 is 4. Minus 3 times 4 is 12. X to the 4 minus 1, which is 3. 2 times 3 is 6. X to the 3 minus 1. 7 times 2 is 14. X to the first, and then the derivative of 2 is nothing. Do it again, second derivative. 4 times 25 is 100, x to the third, minus 36, x to the second, plus 12, x to the first, plus 14. Now the third derivative and first answer here. 100 times 3 is 300, x squared, minus 36 times 2 is 72, x to the first. The derivative of 12x is just 12, and the derivative of 14 is nothing. So first answer is 300x squared minus 72x. Plus 12. Now do the fourth derivative. So you put a little 4 here in parentheses to mean fourth derivative. 300 times 2 is 600, x to the first. 72x has a derivative just negative 72, and then 12 has no derivative. 600x minus 72. And that's as far as they want us to go here, but the fifth derivative would be 600 because that's the slope of the linear part. The fifth derivative would be 600, and then every sixth derivative and beyond would all be zeros. Okay, so here's the concept about what does a positive or negative second derivative tell you. When you get a graph, we already know about increasing and decreasing, and then increasing again. That comes from the first derivative. But the way a curve is bent is another concept. So if you take y equals x squared, this is a U-shaped parabola. But when you have curvature like this, this is called concave up. It's like if rain fell down in here, it would just kind of pool up inside of here. And you could hold it in that curvature. If it's curved enough, the rain wouldn't fall out. But when you bend the other way, then if you took your rain in a cup like that and turned it upside down, you go from this to that. That's called concave down. Now whatever you're holding is going to fall down. Concave up, concave down. This is what happens when a second derivative is positive or negative. You're concave up or concave down. And then if you switch from concave up to concave down, which happens in the x to the third graph, the x to the third graph is concave up on the right side of 0, but it's concave down on the left side of 0. And right at the origin, that's the spot, the one and only spot here, where the graph is switching from concave down to concave up. In calculus, that's called a point of inflection. Point of inflection. Inflection point, sometimes they call it. Point of inflection. These points of inflection, these are like relative maxes and mins in the first derivative. You can only get these points at places where the second derivative is 0 or undefined. So that's what's nice is we're going to solve for the second derivative. We're going to set it equal to 0 and or look for any spots that are undefined, as long as they also aren't undefined in the original function. And that's going to be our list of possible inflection points. Once we make a number line and check each of the regions, then we'll know which areas are positive and negative in the second derivative. If it switches from positive to negative or vice versa, from one side of one to the other side, then you have an inflection point. So searching for inflection points in a second derivative is very similar to searching for local maxes and mins in the first derivative. In fact, if you called this one f of x, if the original is f of x, then f prime of x would be 2x. And that's only equal to 0 at 0. 0 is the one and only critical number of this function. And if you plugged in -1 or +1, it would be negative on one side and positive on the other. The graph is decreasing first, hits 0 for a second, and then it's increasing after that. So that is a local minimum right there, a relative minimum. But if I do the second derivative of it, the second derivative is just positive 2. The second derivative is always positive no matter what x you pick. It never equals 0, it's never undefined, so it therefore cannot have any inflection points, and it doesn't because, look, the graph is always concave up. It's always curved in an upward fashion everywhere you go. So this confirms how that works right there. If I do that for this one, the first derivative would be 3x squared, but the second derivative would be 6x. 6x is never undefined, but 6x equals 0 at 0. So 0 is a possible inflection point, but not guaranteed, just like when you find a critical number that doesn't guarantee it's a local max or min. But x equals 0 is a possible inflection point. We already know from the graph that it is, but if we had a more complicated one and didn't know, I would put that on a number line and I would check one number on each side. This is why the first 6 or 7 homework problems they've been having us plug into the second derivative. So f double prime of -1 would be -6. That would be negative. That's concave down. Plug 1 in. 6 times 1 is 6. That's positive. So then you're concave up. And you can clearly see that in the graph. It's concave downward, a downward curvature. Everything on the left of 0. But then it switches to concave up, everything to the right of 0. That is a point of inflection right there. And the process of doing this is very similar to the process of finding local max and min when you're working with the first derivative. If you do this little process right here on a second derivative, then you're checking for inflection points. But the procedure is identical to when you're doing it on the first derivative and you're looking for relative maxes and mins. So they first, on number 7, they're going to make you do this graphically, and then number 8, I think they make you do it with a function, actually. So notice that it increases until about right there, actually. And then it starts decreasing. So a relative max or min is often not the same place where the inflection point is. So you can curve and reach a high point like the vertex of a parabola and start curving still downward. That's still all concave down right there. That whole portion, the relative maximum's here, but the inflection point can be here further down the mountain. And then if this curves upward like that, this is upward curvature right here, it switched from concave down to concave up right at that spot. That's a point of inflection. And the minimum might not be till here. The local minimum is right there. So you often get the local maxes and mins. They're often in different places than where the point of inflection is. And at this point, we're only worried about points of inflection. We're not so worried about the local maxes and mins at the moment. But later we will be. And when we get to section 5.4, then we're going to put all this together in every problem. And we're going to want to use all the tools and all the ideas that are going on in one problem. But right now, this is not about the local maxes or mins. We don't care about that high point or this low point down here. The whole question is this coordinate 1, -11/3? Is that an inflection point or not? Although I guess maybe they don't even want that. Yeah, that's the last part of this. So first it says find open intervals where the function is concave upward or concave downward. It's concave down first from -infinity until you get to +1. So we're concave down on the interval -infinity to +1. Then from +1 forever to the right to infinity, from +1 to infinity, it's concave up. So I usually do these by traveling left to right. You don't have to answer them in order. You can if you want to go, where's all the positive ones, where's all the negative ones, but I usually just travel left to right and it's easier to tell. So it's first concave down, then it switches to concave up. And so that would be an inflection point too. Now, if you did my graph a second ago, this one's always concave up because the second derivative is always positive. And you can clearly tell from the graph it's always concave up. Parabolas are always either all concave up or all concave down. They don't do anything else. So it's possible you could say the graph is concave down and it's never concave up or vice versa. That's why they have options for that. Or if you just have a line like a linear graph, linear graphs are not curved at all, so they're never concave up or down. They're just straight. Or if you get an absolute value, there's no concavity to that either. So you have to be curved or bent to have a possibility of concavity. And the inflection point is literally this point in question. It was either going to be that or nothing, because that's the only one that we had on our given graph here. And it is an inflection point because it's concave down on one side and concave up on the other. Now, one slight difference compared to what we were doing procedural-wise last time is if you're increasing first and then you decrease second, that's a relative maximum. If you decrease first and then increase second, that's a relative minimum. So when you're working with the first derivative, you actually care about which one is which. It matters if it's a min or a max. You get it wrong if you put the wrong one at the wrong time. But inflection points, we don't have a distinction between the names. You're an inflection point whether you're concave down first and concave up second, or vice versa. If it's concave up first and concave down second, it's still an inflection point. It doesn't have a separate name. That is the one difference here in this concept. Okay, now let's try to do it without a graph given. It's the same directions. When is it concave up? When is it concave down? Find any inflection points, but now we're going to do it from a polynomial. Here's number 8. F of x equals -3x cubed plus 5x squared plus 174x minus 6. So first derivative is negative 9x squared plus 10x plus 174. If I found the zeros of that, there could be two zeros. There could end up being two relative extrema, and maybe one's a local max and one's a local min. That's probably what's going to go on there. But we're not doing that at this time, so we're going to skip that. Go right to the second derivative, negative 18x plus 10. The second derivative is linear, and it's a polynomial, so it can never be undefined. And it can only equal 0 once, so I have one chance to have an inflection point. Solve this for 0. Those both divide by 2, so 5 over 9. So make a number line with the only one on the number line is going to be 5 over 9. I would plug in 0 for something smaller than that. I would plug in 1 for something bigger than that. 5/9 is in between 0 and 1. Plugging zeros in are nice because you're just going to get this. The second derivative is positive for any number smaller than 5/9 because 5/9 is the only chance it has to switch. So we know it's 0 at 5/9. Anything to the left of that, they all have to be the same. And once you check one of them, whatever that one is, any other one that you would have checked would have the same answer. So the second derivative is always positive when you're less than 5/9. When a second derivative is positive, that's when you're concave up. Plugging 1 in, negative 18 times 1 is negative 18, plus 10 is negative 8, so it's negative anytime you're bigger than 5/9. So it is switching to concave down. From negative infinity until you hit 5/9, that's when you're concave up. So this time the concave up is happening first. The graph is concave up from negative infinity until you get to 5/9. And then from 5/9 all the way to positive infinity, then it's concave down. It only has the one switch. So 5/9 is the location of the inflection point. It's the x value of it, but we don't know the y value yet. But I can put half the answer in. It's 5/9 comma something. Unfortunately, plugging 5/9 into this would be messy. So that would help to have a graphing calculator. And if you have one, you can just type it in with parentheses around the 5/9. So I'm going to put 5/9 into the 3 x's. Negative 3 parenthesis 5 divided by 9 parenthesis raised to the third power. Plus 5 parenthesis 5 divided by 9 parenthesis squared. Plus 174 parenthesis 5 divided by 9 parenthesis minus 6. So just putting 5/9 in those 3 x's, press equals. It's a big messy decimal. But good old math, enter, enter, turns it into a weird fraction. But I don't care how weird it is. 22282 over 243. That would have been really hard to find without a graphing calculator. And certainly nobody would have ever guessed that fraction either. 22,282 over 243. That's the inflection point, the spot where it switches. Now we know from our college algebra knowledge, hopefully, we know how negative x cubed graphs sort of look like. They're the opposite of this one, actually. So negative x cubed decreases first, increases, and then it decreases again. Because its end behavior is rises on the left and falls on the right. There's going to be a local minimum first, a relative minimum. followed by a relative maximum. This is like that problem 9 in the last section that had the endpoint issue. But it's concave up all the way till about there. There's upward curvature where you could pour water in here and it would stay in here. But once you go here and beyond, now it's upside down. Now it's curved downward. If you tried to pour water there, it would fall out. So that's the inflection point right there. It's often not at the same place where the mins and maxes are. The minimum's here, the maximum's there, but the inflection point's somewhere between the two. It's not always halfway between them, but somewhere between them. And then finding the location of it's easy. It's the y value that can be hard sometimes to find. But if you have a graphing calculator, then it's pretty easy. Okay, so now here's a second option you have when you go back to section 5.2. And when we move forward also into future sections, it turns out that you can tell if a critical number from the first derivative, if you find all the critical numbers from the first derivative, if you then check them with the second derivative, you can find if they're maxes or mins in one calculation each instead of two calculations each. So that's what we're going to do on this problem, number 9. In fact, I'll do it both ways to show it to you. So 3x cubed minus 6x squared plus 5. This problem is kind of section 5.2 and 5.3 all rolled into one. So first you find your first derivative. It's a 9x squared minus 12x. Then you'd want to find any critical numbers from that. And it's never undefined because it's a polynomial. It's squared, so it could have 2 zeros. There could be 2 critical numbers here. In fact, there will be. There's a GCF of 3x, leaving 3x minus 4. One of the critical numbers is 0 itself, and the other one you'd have to add 4 and divide by 3. So the other one is 4/3. 0 and 4/3. Here's your two options. You can put 0 and 4/3 on a number line. And then you could check -1 and +1. If -1 has a different plus or minus than +1 does in the first derivative, if it's positive first, negative second, or vice versa, then you know that there's a local min or max there, but you need to check both to know that. You'd have to calculate both f prime of -1 and f prime of 1. Now, neither one of them is all that hard to do, but in some cases, it can be long and complicated to do that. And then when you are done with that one, then you would have to try, then you reuse this one. You would reuse f prime of 1, but then you'd probably need f prime of 2, or whatever you want to pick bigger than 4/3. You would need to see both of those to tell if there's a min or a max at that point. So for any given spot, any given critical number, if you want to know if that's a local max or min, you really need 2 calculations to tell per critical number, even though you're kind of sharing this middle one. So I'm really only doing 3 total calculations, but I'm really using two at a time. The other option is if the second derivative is easy to do, which here it's very easy to do. If the second derivative is easy to do, it's often less work to check for maxes and mins from it, even though the second derivative is usually used to check for concavity. So if you do 9 times 2, 18x, and then minus 12, there's a completely separate idea here. If I were to work with 18x minus 12 and set it equal to 0, I could search for inflection points. And I can tell when the graph's concave up, when the graph's concave down. But I'm not doing that on this problem. What this problem wants is really what section 5.2 asked is there any relative max or mins? So it turns out if you take critical numbers and directly plug them into the second derivative, weirdly the second derivative, the critical numbers came from the first derivative, but I'm going to plug them into the second derivative. We never plug critical numbers into the first derivative because we already know what they're going to equal. They're definitely going to equal 0 if you plug them in there. It's pointless to plug 0 or 4/3 into the first derivative because we already know those are the two numbers that make it 0. But if you plug them into the second derivative, and that's real easy here, this disappears, this is -12. In one calculation, I can tell that that's a local max or min, because we know that if the critical number, that had to either be an undefined or a 0 slope on the original graph. And if you're 0 or undefined at a certain spot, then you have a chance to be a max or a min. And two ways to decide are if it's increasing on one side and decreasing on the other. That's one way to tell. But if you know you're concave down at that spot, this is telling me that if I plug 0 in to the second derivative, that the second derivative is concave down at that spot. The original graph would be concave down at that spot. If you're concave down at a spot where you know the original graph is either undefined or flat, well, that's a local maximum. That has to be a local maximum from one calculation. I didn't need two calculations to tell. That's a relative max because it's curved downward, so it's going to be like an upside down parabola and have a high point. And then the second derivative at 4/3 is a little harder to do, but even in a basic calculator, you could type 18 times 4 divided by 3 minus 12. 18 times 4 divided by 3 minus 12. It's positive there, positive 12. That means it's concave up. And if you're concave up, if you're just concave up in general, that doesn't tell me it's a max or a min. But if you're concave up exactly at a critical number, right at that spot where it's kind of flat, that's a relative minimum. Because you're going to look like this. And if you know that's a flat spot, then it has to be a minimum. So what this tells me is, and we know this from our algebra knowledge, positive x to the third graph looks like this. So it is concave down first from there to there. It's going to be concave down all the way to there. And then it's concave up the rest of the time. And that was confirmed right here. And that's an inflection point, although I don't really care about that for this problem. But when you're concave down at a spot where you know the slope is 0 of the tangent line, the derivative is 0, then you know that's a local maximum. And if you're concave up at a spot that you know the derivative is 0 and is a critical number, then that has to be a local minimum. So I could have done f prime of 1 and f prime of -1, and what would have happened is I would have found out that it was increasing first and decreasing second. That's what would have happened if that's the first derivative test. But in the first derivative test, you need to check both sides of that. You need two calculations to answer that. This is called the second derivative test. The second derivative test is when you plug critical numbers of the first derivative into the second derivative. And in one calculation, if they come out positive or negative, then you know there's a local max or min there. And it's easy, just draw a sketch of it. If you're concave down, you're going to have a local maximum. If you're concave up, you're going to have a local minimum. That's real easy to just sketch that quick and know that. The only downside to it, there's two downsides. One is if the second derivative is going to take you a long time, like say it's a product or a quotient rule, then I wouldn't waste time doing that. Then it wouldn't really save any time. It would take more time, actually. And the second one is what they mentioned here. If you plug these critical numbers into the second derivative, even though they came from the first derivative, and you get 0 or undefined in the second derivative, then it's inconclusive whether they're maxes or mins. And then you have to go back and do the first derivative test anyway. So it's up to you on a given problem. You can do the first or second derivative test. They'll always give you the same answers, except for in this rare case when it is inconclusive. But it just, for me, it comes down to how much work do I think it's going to be to find a second derivative. If I can do a second derivative real quick, like with a power rule, or even like an e to the x that's real quick, then I would rather do the second derivative test because there's a little bit less work in calculating things. So we had two critical numbers here, 0 and 4/3. And we are going to do this again in section 5.4 when we put everything together. So when we're doing 5.4 in the next video, you'll see sometimes I'm going to work with the first derivative test, sometimes I'll work with the second. It might not be on a test if you have the time. You might want to do both in the same problem just to confirm everything. Okay, we have a 0 was the local maximum. And do they just want the location of it or the whole location and value? It looks like they just want the location. So that helps. I don't have to waste time finding the y values. There's a relative maximum at x equals 0. That's the one that happened first. And then the minimum happens second at 4/3. But they're just having you answer the minimum first and the maximum second. They don't care about the order of it on the graph. There could have been just a minimum or just a maximum, not the other one. But we got one of each. So you'll see this more in the next section as well, too, is the good news. And then here's a business application of this. It turns out in business that if you have, say you want to spend money on advertising. Everybody knows advertising works. Otherwise, why do they spend money on billboards and TV commercials? Why do they spend millions and millions of dollars to have a Super Bowl ad? If that didn't work, the companies wouldn't waste money for that because it's millions and millions of dollars at the Super Bowl. But it turns out if you just throw a bunch of money at an advertising campaign, there reaches a point where you're throwing money away, actually. So if your advertising is working at first, you're going to be concave down, where more money you put in, the faster and faster it's going to help you gain profits. Or maybe I'm saying that backwards. Maybe it's like this, where it's getting faster and faster and faster. It's growing. So that's why they spend millions of dollars hoping to get new customers. But then enough eyeballs see it, you're going to run out of customers eventually. So then you hit an inflection point and it bends the other way. And now the more money you spend, the less you're getting in return. So this inflection point is also in business called the point of diminishing returns. The point of diminishing returns. Returns are profits that you're making. So up to a certain point, it's better to spend more and more on advertising. And then after that, if you spend too much on it, you still make profits, but you're outspending the profits is the issue. So you're losing profits you're still bringing money in, but you're spending it faster than you're bringing it in. So here's a business application of an inflection point. Is if you can find an inflection point, that would be your ideal amount of money to spend on advertising or whatever you want, whatever this happens to be about. So find the point of diminishing returns, and they want both the x and the y. They want the location of it and the value of it. R of x represents the revenue. Revenue is how much money you're bringing in thousands of dollars. X represents the amount spent on advertising in thousands of dollars. So if you want to do Super Bowl ads, then you'd put millions of dollars instead of thousands of dollars. So their revenue is what they're watching. They're watching how much money they're bringing in, and they know how much they're willing to spend. Does the revenue have an inflection point? If so, we want to hit that exactly. If we can hit that X exactly, that's our best bet to maximize our profits. And if we spend more than that, we're just throwing money away. Then our returns start diminishing. Okay, and X goes only from 0 to 20, so maybe they only have $20,000 in their budget for any kind of advertising. So since X is in thousands of dollars, if the X has to be between 0 and 20, that's $0 and $20,000. So the marketing department, they've been given $20,000 is the most they can play with. But if they spend it all, it might not be the maximum profits, actually. That's the whole point of this problem, is that you don't want to just throw all the money at the situation. So find your first derivative. Derivative of a constant's nothing. Then I'm going to get a negative 3x squared, a 72x, and a 700. So then let's find the second derivative. This is not about maxes and mins, so I don't care about critical numbers right now. And then do the second derivative, negative 6x plus 72. So when does this equal 0? Because it's definitely never undefined. It's polynomial. And it's going to equal 0 only once. So we have one possible inflection point. And if it is truly an inflection point, then it's also in the business setting, it's also a point of diminishing returns. X equals 12. So possibly $12,000, that might be our ideal amount to spend on our advertising if we want to maximize our profits. Okay, so make a number line. Here's 12. I'm going to pick 0 and 13. And you plug these into the second derivative, not the first or second, or first or original, I mean. Put a 0 into the second derivative. And that would make this 0 plus 72. The second derivative is positive all the way up to 12. And that's concave up. So it's looking like this up until 12. Concave up. So at first, if they only spend a little bit, they're not really increasing their profits, but then there reaches a point where, okay, now the market's been flooded with our name and advertising, and now people are interested, and now all of a sudden it's hard to keep up with the demand. People want to buy our product, and it's going faster and faster at first. But then when you plug 13 in, negative 6 times 13 is negative 78, plus 12 is negative 6. It's negative there. So after $12,000, now it's concave down. So it's slowing down in how fast people are buying our product. That is an inflection point because it was concave up first and then concave down second around a 0 of the second derivative. So when you have zeros of the first derivative, they're called critical points, critical numbers. They are chances to have local maxes and mins. When you have zeros from the second derivative, they're chances to have points of inflection, but they don't have a name like critical number. They're kind of like a critical number, but we just doesn't have that name. So yes, $12,000 or 12x, because x's are in thousands, that should be the point, the location where the diminishing returns hits. So we would ideally want to spend $12,000 on advertising, and then we could save the other $8,000 for something else. And then they do want an ordered pair. They do want an XY. So now whenever you want the Y value, it's always from the original, never from any derivative. So I'm just going to plug 12 into where these three X's are right there. 10,000 minus, plug in 12, raise it to the third power, plus 36, plug in 12 and square it, plus 700, plug in 12. So again, I don't know how well you can see that here, but... And it came out to $21,856. So if we spend $12,000 on advertising, our profits will be, our revenue really, not profits, but revenue will be $21,856. So we bring in $21,000 by spending $12,000. That's why people advertise. Your profit would be subtracting those two. $21,856 minus $12,000, that's how much profits you made. But if you kept going beyond $12,000, the profits will start decreasing they won't keep increasing at the same rate that you're spending your advertising at. So the two graphs will start getting closer and closer together, and it's just you're just throwing profits away by doing that. So that was section 5.3, and we got all 10 of them done now. Save this. Okay, so we did 3 videos this week. We have now finished 5.1, 5.2, 5.3. Next week, we're going to do 5-4, 6-1, and 6-4. The week after that, we'll do 6-5 in the first half of the week and review in the second half of the week, and that's when the test is. So that's it for this first of 3 weeks. We've done 5-1, 5-2, and 5-3. See you next time for 5-4.